All right, thank you for having me. I'm going to talk about our work on single atom catalysts on amorphous supports, particularly focusing on the Phillips catalyst, but also showing some methodology improvements that can probably be useful for a lot of different systems. The work that I'm going to show was predominantly done by Dr. Chang-Hae Andrew Kim, shown here, but it was enabled by many prior efforts, former graduate students, Salman Khan, Craig Vandervelden, Armin Shasta-Zeta, Anthony Fong, Brian Goldsmith, along with collaborators, Professors T. Ellens, Susanna Scott, Marco Caricato, and Ward Thompson. All right, so let's start by looking at the landscape of things that people study in catalysis, and particularly computational side of catalysis. There's a lot of beautiful work that's been going on for many decades, focusing on acid-base catalysis and homogeneous catalysts. A lot of nice work on enzymes. On the heterogeneous catalysis side, there's a lot of ongoing work now and tremendous amount of things to do, hard calculations to perform, looking at metals, metal oxides, and zeolites. These, I want to point out, are crystalline materials. And the structure is known, and oftentimes the same sites are found repeatedly throughout the material. And there's a long-standing recipe for doing calculations in these areas, even though the calculations are extremely difficult, and there are sometimes some very complicated effects to account for. In the worst cases, sampling issues that have to be resolved. There are also disordered catalysts, which include a couple of different categories themselves. And so these can be dynamically disordered, like the work that Anastasia Alexandrova does with the fluxional subnano clusters. There can also be quench disordered catalysts. And those would include things like metallic glasses, which I won't really talk about, and also the very prevalent single metal atoms attached to amorphous silica, often known as supported organometallic catalysts. I'm going to focus on the Phillips catalyst, and of course that makes most of the world's polyethylene, but it's not the only one. There's actually a lot of industrial processes at large scale that are running using these catalysts. So you've got molybdenum on silica, which is used in the Shell higher olefins process for metathesis. You've got olefin epoxidation processes that run with titanium on silica, partial oxidation of propane that's being done with vanadium on silica, and you have hydrogenolysis, which is potentially of future interest, looking at polymer upcycling applications. That's of course work in progress with Sado and Del Ferro. I want to point out that if you look down this list at the people that I've listed who study these things, they all have one thing in common, and that is that they are experimentalists. This area of catalysis has lagged far behind in computational advances from some of the other areas in catalysis. And that's because when we talk about an amorphous material, we don't necessarily even know how to begin. It's an unknown distribution of structures. Experiments can only do little amount to help us, and that really complicates things. What do we know about the Phillips catalyst and how it works? Well, the grafting mechanism is laid out here across the top. We think of it starts out with these vicinal silanol groups, and they react with a chromochlorate precursor, release HCl, and give you these chromochlorate groups on the surface. Those can further react to eliminate one of the two chromochlorate precursors to give you a bidentate chromium oxide, a chromium oxo 6 cluster on the surface, to give you a chromium 6 oxo group on the surface. And then the next step is that you have to take that chromium 6 oxo and you have to reduce it. So that's either done with ethylene itself or with CO, and that takes you to this chromium 2 site on the surface. And then here's where the mystery happens, right? So it's not ever clear how you go from this chromium 2 site on the surface right here to the putative active site, which is a chromium alkyl 3 compound on the surface. And that's still an ongoing mystery. We have published some papers putting forth a computationally viable route that explains some experimental observations and doesn't seem to have, at least at this stage, any evidence against it. But also see work by Al Stiegman and coworkers in 2020. They provided evidence that if you track the amount of this chromium 2 site that you make, it ends up corresponding closely to the amount of the active chromium 3 species in their experiments. And so we're going to assume, based on that experimental work, that this is a quantitative conversion, that we basically can take all of the sites that end up being grafted, end up here at the chromium 2, and they end up being these chromium 3 alkyl sites. Once you have that chromium 3 alkyl site, there's a lot of computational evidence and quite a bit of experimental evidence that the chromium 3 polymerizes by this very simple Cauchy-Arlman mechanism. Adsorb an ethylene, you insert an ethylene into the chromium carbon bond, and then you go and you do it again. The chain is now one link longer. 2 links longer technically. The evidence on the computational side in particular is that it polymerizes at about the right rate, and it generates chains of approximately the right length in this work. And when you consider those routes, we also draw those things in an oversimplified fashion as though all these vicinal silanols are perpendicular to the surface, sticking up in very regular fashion. The reality is that these stick up in all kinds of different directions with different distances between them, and it's a pretty complicated ensemble of silanol groups that you start from. And that's well known in the literature, right? So McDaniel has pointed out that all sites should be a little bit different, and that small fraction of them are active from active site counting techniques. That you have a quench distribution of sites that's unknown, and that spectroscopy techniques mostly are going to reflect if only a minority of sites are active. The spectroscopy is going to see the majority of them and potentially give you even misleading conclusions about the structure of those sites. So if we want to make computational progress towards understanding how these catalysts work, we want to answer 2 questions. Where does grafting occur? And which of the sites that get grafted will actually end up being active for polymerization? There are 2 things that are really going to help us do this. One is that we can actually afford accurate DFT calculations for these systems. I say this to push back on the notion that we shouldn't try to do accurate calculations. We can afford to do a fairly high-level hybrid DFT with really good quality basis sets. We can do fully optimized transition states and intermediates for all of the species along the reaction pathway, the full catalytic cycle for each of the sites on my surface. We can include all these various factors, rotation, vibrations, in the transition state theory calculations. We can do the rigorous energy span and pseudo steady state approximation type rate laws at every site. And finally, we can even account for conformers of how that alkyl chain comes out and interacts with the site, potentially forming things like agostic interactions. Those are all things that we've included in this analysis. What I would argue that we cannot afford to do is to use a naive treatment of the site disorder, right? So you have the smallest activation energies in this distribution of activation energies that you're going to see on the surface. They are exponentially more important than the ones in the middle of the distribution. And calculations show something like a range of on the order of 20 kcals per mole of activation energy values. And that translates to a range of activities that spans like 10 orders of magnitude. 10 orders of magnitude is an enormous difference. It's not something that we want to ignore or dismiss as a futile effort to get accurate calculations. If you're off by 10 orders of magnitude in your calculation, then you're really not predicting anything useful. Off by a factor of 10, we might be able to live with. Off by a factor of 100, we might even be able to live with. But 10 to the 10 is just beyond the range where anything that you can say about the mechanism should be trusted. So let me give you an example showing the effects of this range of activation energies. If I want to compute the average activation energy, a key connection with the experimental observations, then I take the derivative of the log of the site averaged rate with respect to 1 over kBt. This calculation, if I bring that derivative inside the integral here, and remember that k is like an Arrhenius factor, behaves almost like the Boltzmann factor in equilibrium statistical mechanics, right? So rho of x here is my site density, and k is my Arrhenius factor. Whereas in equilibrium statistical mechanics, I would have a density of states and a Boltzmann factor. This is basically giving us very similar calculations that parallel closely equilibrium stat mech, and it shows you that the distribution that you should sample in order to get the correct answer is not actually rho of x, it's rho of x reweighted by k of x. And that is an easy thing to miss if you're not paying attention to the math and how to do the calculations for these systems. So what matters here, and this is the point that I really want to emphasize with this slide, is that the overall catalytic rate is a result of the activities and the abundances multiplied by each other. So this effort, I hope you will view not just as an effort to compute accurate rates, but an effort to properly account for abundances of sites at different strata in the distribution of activities. Going back to this procedure for calculating the average activation energies, there's a wrong way to do the calculation where you'll never get the right answer, and that's the straightforward arithmetic average over sites. It's never going to converge. There's a slow way to do this calculation, and that is to k reweight your straightforward ensemble each time. And that, we have shown, takes hundreds of thousands of values of these rate constants in order to converge. And then there's a fast way of doing this, which is guided by the math in this little calculation. That's to importance sample the distribution rho of x, k of x, while simultaneously learning the value of this k of x map. notice the semblance to equilibrium statistical mechanics where we have to sample very similar distributions and we use Monte Carlo methods. It has been kind of surprising to me that these ideas have been so slow to take off. The exact same analogous arguments motivate, treatment of quench disorder with the importance learning framework. So the point here is that you can't just pick the Silenol geometry you like. Grafting is selective. It's going to choose the environment that it wants to pick, and for us to make predictions about the abundance in that ensemble of sites, we have to know something about how that grafting mechanism is sensitive to the local Silenol environments. This is work done by Salman Khan, a former PhD student. You start from a model of silica. We use the huge models by Ward Thompson's group at KU. We go find all of the little vicinal Silenols on the surface. We carve them out and cap them, and that creates these little examples of Silenols. And you can measure their geometric properties, and you can get the distribution of different geometries on the surface of that material. So now we know already something about the abundance of different structures on the surface of our silica model. But now, how do the activities vary from one geometric descriptor to another? Well, we actually do the full map of the grafting pathways, is what I'm showing here in the upper left, for all of these things. So we're optimizing all 4 of these intermediates and the transition states between them and solving a little microkinetic model. And then we use that in a population balance framework to get an idea of how the sites at each geometry phi evolve in time, and you could see they're all doing different things at different times. Some graft early, some graft late, some never want to become state 4, some get stuck in state 3, and that is information that we can really encode quite efficiently, and we can integrate it to get an idea of how many sites in each different state you have as a function of time as the system evolves. So the importance learning algorithm part of this is, to my knowledge, the very first combination of importance sampling with machine learning. It begins with a little training set, randomly chosen sites shown here as a smattering in blue. This is we're taking those sites and we're training a machine learning model to predict the activation energies based on the local structure of those sites. Then we use that trained model to reweight the distribution. Remember, we want to compute the activation energy and reweight the distribution by that exponential factor. And then we want to sample not the blue distribution, but the orange one. And then after we sample that site, we do new DFT calculations. And we use it, we add it to the training set, and we retrain the model and check to see whether we've actually converged, whether our predictions from the model are actually changing anymore. You could see that it only takes tens of iterations, and it's basically converged on the correct answer. Added training data, they become the red points, and it's no coincidence here that the new points are systematically lower in activation energy than the ones that we started with in blue. The blue ones were sampled from that initial distribution. The algorithm is learning to identify sites on the tail of that distribution, and those are the ones that are in this orange distribution already. Armin Shayasta Zeta, shown down here in the lower right, took this machinery, which at the time of Craig van der Velden's paper was limited to kind of little model systems, and really coupled it to ab initio calculations for the first time. So that we're beginning to do things with real chemistry, arguably not real catalysis yet. That's a zeolite. It is a catalyst, but it's not doing anything catalytic here. And yet you can compute the ensemble averaged equilibration time between these proton positions, something that can actually be measured. But the point here is not any specific agreement with experiments, just to demonstrate that, if you have water in this system, you get a multi-step pathway. And so we were able to put in multiple steps and make the training process, optimize multiple activation parameters, incorporate transition state theory, a lot of things that sort of brought this whole process a little closer to the language of chemistry and the ab initio machinery for doing this in concert with those tools. And you can see that it works extremely, extremely well. It's converging, again, on the order of 100 iterations, and you really can't see any noise, any error in our predictions anymore. Whereas if you just started with random sampling and used those randomly selected sites on your surface to train a machine learning model, it takes a very, very long time because you're sampling the blue distribution. At best case scenario, trying to reweight that's what we've done here. It's hard to even say when this will converge. I say it's 100 times faster to use machine learning, but we're not even really sure how long it takes for this blue to converge. Okay, so now let's talk about what is the rate law for our particular system, and what are all the parameters in that rate law that are going to vary from one site to another. We have two processes in order to incorporate an ethylene molecule. It has to diffuse through the polyethylene that's accumulated around the active site, and there's going to be some diffusion controlled resistance for that. It's going to set an upper bound on the catalytic rate. And then there is a additional resistance. Of course, the one we usually think about is that you have the adsorption and the insertion process, a two-step catalytic cycle here. And that's the resistance shown here by a typical Langmuir-Hinshelwood looking rate expression. So both of those two resistances are added in here like a resistance in series formula, and then that gives us a partial diffusion control expression that we use to compute the catalytic rate of all of our sites. So this piece is here just because, if the barrier becomes really, really small, then transition state theory will predict rates that are impossibly large. So each site's overall contribution to the rate, now I have to think about not only how fast is that site, but what is the probability that that site would have been grafted. Recall that it was very fast to reach this state 3 in my grafting process, but then the slow step was to convert those into state 4. And so that rate constant, Kg, is the site-specific constant for this particular step. It's a unimolecular decay, and so pretty simple to describe, and we get a simple Poisson expression for the probability that that site will be grafted after some time under a given temperature. And one of the things that the experimentalists have varied, one of the things that experimenters have varied in the literature is the temperature at which this process occurs. So now what we do is we take that probability that the site has been grafted, we multiply it by the R cat from this expression, and we get an overall effective contribution of each site on our slab of silica to the reaction rate. Now what we want to do is to incorporate all of this into importance learning. So that R effective remembers the site-specific properties K1 and K2 that appear in this mechanism, and it remembers the site-specific property Kg that appears in this grafting probability factor. And what we're going to do now is to train a machine learning model to predict all of those pieces as we go through and construct that rate expression. And that rate expression now is what we're going to importance sample. We're going to be looking for sampling new sites according to that overall effective rate. We start with the random collection of sites, we importance sample, we do new ab initio calculations, we keep going around the cycle until we converged, and that's where the results that I'm about to show you come from. These are the results shown here on the left. This is our site averaged rate, fluctuating at first, but gradually getting better and better as I accumulate more and more sites in my library, my training set. You can see that it evolves differently whether I do the importance learning with the grafting probabilities computed for 200, 400, or 600. In all of these cases, the catalytic rates are computed at 100 degrees C. I think that it's a neat thing that the importance learning framework is able to do. It's able to take this multi-part process where you prepare your catalyst and then you use your catalyst, and I can simultaneously train to account for both of those two processes in a systematic way. You'll notice that at 200 degrees C, 85% of my sites get grafted. At 400 degrees C, 96% get grafted. And at 600 degrees C, 99% of my sites get grafted. And what's happening here is that the site averaged rate is going up as that temperature of grafting goes up, and that's because the sites that resist grafting the most, that take the highest temperature to coax them into driving off that last chromium chlorate and becoming that bidentate active site, those sites are the last ones to graft are the most active. So you have this anti-correlation between the ease of grafting and the catalytic activity on the surface. And that's something that we didn't really know. I mean, it's been talked about that maybe it exists, but here you can see in computational evidence behind it that it really does. So the kinetics are dictated by many mediocre sites when you do your grafting at low temperature, and they're dominated by this handful of very, very active sites, the most resistant ones to graft when you do it at 600 degrees C. The most active sites here are among the least likely to be grafted. All right, so one of the things that was really exciting and rather unexpected is that experimentally, they also see that as you increase the grafting temperature, you can change the overall activity of this catalyst by 10 or 100 times. So we're somewhat in the ballpark of predicting the right the right effects of that grafting temperature on the overall activity. And this is what's really surprising, and maybe just a coincidence, we're only about a factor of 10 off from the actual site averaged rates that are measured in the experiments for the real Phillips catalysts. So all of these things bode well. They suggest that we're in the range of reality. That degree of agreement might be fortuitous, but it does give us some confidence that we're probably on the right track to be able to model these things and interpret them. We have done a lot of structural analysis, combing through these different structures, looking for key differences, examining all kinds of trial coordinates to try and reduce the dimensionality of this mapping from all of the geometry descriptors. The locations of the anchors to the surface are our basis set here. We want to reduce that relatively high dimensional space. I think it's only 6 dimensions actually. We wanted to reduce that down to a one-dimensional map and be able to predict the rate of grafting and the rate of the catalytic activity of each site. But we were unable to really find a simple geometric description of this. The best we could do is say that the catalytic rate and the grafting rate themselves sort of organize everything nicely. Now, it is one of our goals to find a geometric description of the catalytic reactivity in these systems, because if we could, then we would find those sites that result in the most active sites, and we would say, well, just make a homogeneous catalyst that looks like that, right? If you can make a homogeneous catalyst that always has that geometry, then you can get around this. Dispersion of active sites on the surface. To that end, we did a kernel principal covariance analysis, and that shows that indeed you can reduce the dimensionality. In hindsight, we maybe should have recognized this, that if you're trying to describe two functions of geometry, you shouldn't hope that you can do that with one map. So these two covariates allow us to describe everything that's happening on the surface. You can see they describe both the landscape of catalytic rates and the landscape of grafting rates. How do you know that they're working correctly? Well, when they work poorly, if you choose the wrong coordinates and you try and make a scatter plot like this, you see the blue and the yellow all mixed together. When they're working correctly, you see very, very clear gradation in these points with where they're located on this surface. And that means that those two coordinates are able to distinguish where you are in this space of grafting rate and simultaneously where you are in the space of catalytic rate. And of course, if you can describe those two things, then you can describe the overall rate because it's a product of the two. Do the activities follow a BEP relation? I mean, that was one thing that we really hoped. We hoped that maybe for the catalysis part alone, we might be able to get a very simple correlation with activity by looking for the Bronsted-Evans-Polanyi relationship. So why would that help us? Well, you've got a two-step process in the catalytic cycle. I adsorb an ethylene and I then incorporate an ethylene. So I've got insertion and adsorption. And when I do the whole catalytic cycle, my alkyl chain has gotten just 1 unit longer. And so that shouldn't really depend, the enthalpy for that transformation overall shouldn't depend on the geometry of the site. But how the insertion and adsorption parts of that overall cycle balance each other to give you the overall delta H does depend on the active site. So the thinking was, if we could use a BEP relation to get a correlation for, say, the insertion step, because of Hess's law, we would also have a correlation that gave us a simple descriptor for the adsorption step. And then we would have the ability to construct the pseudo-steady state rate expression. The pseudo-steady state approximation now tells me that I can replace both of those two site-dependent properties by an insertion enthalpy-dependent property alone. And that was the goal. Unfortunately, the insertion enthalpy barriers exhibit no correlation with insertion enthalpies. Okay, so I'm going to go ahead and wrap up here. I'm going to recap some of my conclusions. Importance learning is able to tell you about site-specific grafting rates, insertion rates, and ethylene adsorption rates for an ensemble of these isolated metal centers on an amorphous catalyst. This is a really transformational capability. We did this for an ensemble of 250 sites where all the previous best efforts were maybe 3 or 5, just a handful. We began from the best silica models available. In the ensemble of initial silanols, grafting probabilities we found are anti-correlated with the resulting catalytic rates. The most active sites require high temperatures to be grafted, and this causes, in accordance with the experiment, I didn't talk about that along the way, this causes the overall activity to increase with the grafting temperature. Let me just briefly say here, The absolute rates and trends are in reasonable agreement with the observations. That was unexpected and really nice finding. The BEP does not explain the site-to-site activity variations. And finally, we were unable to find simple geometric descriptors, but kernel principal covariance analysis shows that there is a 2D descriptor. You only need 2 coordinates to describe this overall process. We are still looking for a simple, physically interpretable description, but what we're going to do is publish the actual library of sites and all of their microkinetic models and their rate parameters optimized by DFT, and that should allow the community for the first time to actually play with one of these databases and use the and use these tools for identifying the important degrees of freedom and dimensionality reduction. I want to thank the DOE. They supported this work through many years. I'm hopeful to manage to secure funding from them again. I want to thank Dr. Kim for the incredible work on this project. I want to thank all of the former students and former collaborators who have contributed to this work along the way.